Welcome to MECE 3321, Mechanics of Solids. It's sample problem number 2. So let's go ahead and get started. This was a suggestion by Ms. Ramirez to do a problem in which you have a moment located somewhere along the beam, not at the edges, but somewhere intermediate. So let me go ahead and get started. And this is a suggested problem that she had. Hold on, let me do this a little bit faster. 1 second. There you go. Snap of the fingers, it appears. All right. So this is our difference right here. We're not going to worry about distributed load on this particular problem. We want to make it as easy as possible and introduce. There you go. This is let's say 30 pounds. There you go. So it is a cantilever beam, 12 foot long. We have a load of a point load of 40 pounds upward at point B, 6 feet from the wall. We have a moment of 50 pounds foot located at C. That's where it's being applied. And then we have a 30-pound point load located at the very end on point D, 12 feet from the wall, which is at point D again. All right, so remember that step 1 always requires for us to solve step 1. All the reactive loads. So if we draw a little small free body diagram, this right here is our 50-pound foot. This right here is our 30-pound load, 40-pound. This is, of course, 3 feet, 3 feet, 6 feet. And of course, at the base, at the wall, we have reactive force, RA, and a reactive moment. I really don't know if it's located clockwise or counterclockwise. I'm going to call that reactive moment at A. Right. So let's solve for these two, the reactions. So these reactions are solved by sum of the forces in the Y must be equal to 0. So let's solve for RA first. This is positive RA. Positive 40. Negative 30. And I almost forgot. Switch. No, that's it. Pounds. And this, there's no more verticals, so therefore this is equal to 0. And therefore RA is equal to, this is equal to 10. When you put it on the right side of the equation, it's equal to negative 10. So what that tells us is that our reactive load here is actually pushing down. Apparently this is too much. It overcomes this 30-pound force. So our wall is actually has to fight back with a shear, or I'm sorry, with a reactive force of 10 pounds downwards in order to maintain this from moving up or down. So this is our very first reactive force. Now let's solve for that reactive moment at the wall. So for that one we do, let's switch pens, sum of the moments. We can do it about point A. About point A must be equal to 0. I'll consider counterclockwise as positive. So we begin with reactive moment at point A, MA. And then this does not produce a moment at point A. We have 40 pounds producing a counterclockwise moment, which is considered positive. It is at a distance of 6 feet. We also have this. It is known as a free vector. So its position doesn't matter when it comes to finding out the sum of the moments. Only its magnitude. First of all, it is clockwise, so it is negative pound feet. And last but not least, this 30-pound force that produces also a clockwise movement. So it is negative 30 pound. And that one is a distance of 12 feet. And this is equal to 0. All right. So MA equals 2. This, when we turn it to the right side of the equation, becomes negative. This becomes positive, and that becomes positive. And basically, the magnitude of A is 170 pound-feet. And we had it correct. It is positive. So that means that it is counterclockwise. So that one was correct. So from now on, I'm going to be writing RA as a positive number. So what I'm going to be doing, I'm going to be in the new free body diagram, so the sections that I'll be making, I'll be putting a RA, the reaction at A, downward, okay? But that will be for my next drawings. All I wanted to know right now is to find out my reactions. All right, so remember, now that we have our reactions, the next step that we need to take sections. And there's 3 sections that we see here. This will be called section 1. I'm going to call this section 2, and I'm going to call this section 3. And the reason why I separated into 3 sections is because distinct things happen between these sections. Something happens between here and here. There's a moment. Between here and here, there's a load. Between here and here, there's this load. So this will be section 1, section 2, and section 3. And that's when we get to analyze and investigate what's happening internally. So we investigate the internal loadings. And for that, we make a slice, remember. And the slice happens anywhere between 0 and 6 feet. Anywhere between from point A to point B. In other words, where X is between 0 and 6. And we're going to be looking at our very first section, section 1. So we make our cut. There you go. What distance did we make our cut? We don't know. It is some distance X. We just know that it has to be somewhere between 0 and 6. This is still our point A. We still have a reactive, I'm sorry, this one's, remember, I said we were going to call it negative. So by making it point down, so RA equals to 10 pounds. By making it point down, it is already accounting for this negative value right here, right? Because we originally put it up. So there you go. RA is already in its proper direction. MA, we had it right in the first place. It's counterclockwise. It has a magnitude of 170 pound-feet. And then, of course, we have to draw our shear. Always making sure that the shear produces a clockwise movement. Our moment, that always makes a happy face. And that's pretty much it. So let's find out the equations of our shear and moment, our shear and moment equation. So by doing the sum of the forces in the y-axis, where up is considered positive, we start from left to right. RA, that will be negative 10 pounds because it's pointing downward. And then V is also pointing downward. Negative V equal to 0. Make our V positive, and therefore my equation for my shear is equal to negative 10 pounds. All right. And again, this is only applicable from 0 to 6. Now let's do our moment. My sum of the moments about this point right here, which I'm going to call dot, must be equal to 0. And again, I start from left to right. I have MA, which is 170, since I consider counterclockwise positive. And then RA is also producing a counterclockwise movement. So it is positive. that will be 10 pounds. At what distance? That distance is known as x. And last but not least, plus m, which is also being directed counterclockwise. And this is equal to 0. When we solve for m, we leave it there it is, since it's still positive, and we move these two to the right side of the equation, and we end up with m being equal to negative 10x minus 170. And its units are pound-feet. And again, this is only valid from 0 to 6. So we're done with our very first segment, guys. Our very first segment is somewhere between here and here. All right. So let us continue. Let's make a cut somewhere along our second segment, which is somewhere here. We're going to slice it. We don't know where. All right. We just know that there's a 40-pound point load being applied at point B, which is 6 feet away from the wall, that there's a reactive force, RA, of 10 pounds down, a reactive moment, MA, of magnitude 170 pound-feet. And what else are we missing? Oh, nothing else. That's pretty much it. All right. Let's go ahead and add V, M. Again, never forget that this has to produce a clockwise, and this has to produce a happy face. One thing that we're missing is our location, X. That's where we made our cut. We made our cut a distance of X. But in this particular case, X can only be between 6 and 9. In other words, between here and here. This is 6 plus 3, 9. If you're getting a little too discouraged about my speed, I think my students that are very, very fast will get a little disappointed, but the students that are, still struggling with their statics will appreciate this a little bit. But practice makes perfect, guys. So let's go ahead and solve for the equation of V, shall we? So V is solved by doing sum of the forces in the y-axis must be equal to 0. I consider up to be positive. And again, I start from left to right. I have a negative 10 pound. And then I have positive 40. And then I have negative V equal to 0. Put that V to the right side to make it positive, and V is equal to negative 10 plus 40, 30 pounds. All right. Fair enough. Next equation. Sum of the moments about this point right here must be equal to 0. Counterclockwise positive. Positive 170 pound-feet. And then we have RA also producing counterclockwise movement, so that is 10 pounds. It is a distance of X feet. And that's it for that one. Now we have a 40 producing a clockwise, so that will be negative. And it is a distance of, what distance is this? If this is X and this is 6, this is X minus 6. So this 40 is X minus 6 feet. And then last but not least, a clockwise, or no, I'm sorry, a counterclockwise, M, which is plus M equal to 0. Let me check my screen. Yeah, it still comes out on the screen. And this is what we're solving for. We're solving for that m. So m is equal to, and you can do a little bit of simplification. Distributive property here. When these go to the right side, they change signs. But let's see, that's 10 negative 40, that will be 30x minus 410 pounds-foot. You can do the math. You can actually pause the video and check out what the value is. And once again, this is your moment equation, but again, only valid from 6 to 9. And let's do our last section. And I almost forgot to label this section 2, this entire piece. Let's do our last section, section 3. And we're going to be cutting somewhere between C and D. So it's a little bit longer. All right. So at point C, we actually see a moment of magnitude 50 pound-feet clockwise. At B, we see that 40 pounds. And at A, we see RA downward 10. And our reactive moment, MA, of 170 pound-feet. Let's draw our dimensions. From here to here is 6. From here to here is 3 feet. And then from the beginning all the way to where we made our cut, we call that X. Which makes this what? Well, if this is 9 and this is X minus 9. Right here. Last but not least, let's add our shear, always producing a clockwise, and our moment, always producing a happy face, or a smile, I should say. And let's go ahead and get started with solving for our equations. We begin by always stating that this is only valid from 9 to 12. From here all the way up to 12. And sum of the forces in the y must be equal to 0, where I consider up to be positive. All right, and we have negative 10 plus 40, negative 10 plus 40, and that's pretty much it. Minus v. Why did I put w here? Minus v. Equal to 0. That'd be on the right hand side. V is equal to, again, 40 minus 10, 30 pounds. So it has the same value as before. And that's one thing you're going to notice, that a moment, such as this, does not have an effect on our shear. It only has an effect on our moment diagram. Sum of the moments about this point right here must be equal to 0. Counterclockwise is positive. And we begin from left to right. So that will be 170 pound-feet. That's positive because it's counterclockwise. And this RA also produces positive 10 pounds. And it is at a distance of X feet. This 40 pound counterclockwise, so it's negative 40 pounds. And it is a distance of 3 plus x minus 9, which is x minus 6 feet. And last but not least, two more, negative 50 pound-foot, because it is clockwise. Don't forget that it's negative. And then plus m. And this is equal to 0. When we solve for m, this simplifies to, let's see, 30x minus 360. feet. All right, that's our last of our equations. And again, this is only valid from 9 to 12. So let me make a couple of graphs and start producing my shear and moment diagrams. All right, so this is our shear diagram at 6, 9, and 12. 6, 9, and 12. Our x is in the obviously x direction. Its units is feet. And over here we have our y-axis. This is our shear in pounds and moment in pound-feet. So for this very first section, we have an equation. That equation is V equals to negative 10 pounds. So it is constant at negative 10. There you go. And then for this section from 6 to 9, V equals to 30 pounds. And also V equals to 30 pounds. So this goes all the way up here to positive 30. And it goes all the way across as such. And this makes perfect sense. Think about it. Your RA is down, a negative 10. Your force being applied at, let me pull out the original problem. So this is 10, we solve for that. You have 40 pounds up and then 30 pounds down over here. This is your 40 pounds right here, guys. The distance between a negative 10 and a positive 30 is 40, and it's up. And then we finalize it by putting negative 30 over here, which is down. Have to put negative since we're already putting the arrow going down. And this is what your shear diagram should look like. Nice, straight and to the point. Now the second part is a little bit more complicated. The moment equation between 0 and 6, this is 0 to 6, this is 6 to 9, and this is 9 to 12. This is negative 10x minus 170. This is m is equal to 30x minus 410. And this last one is m is equal to 30x minus 360. All of these are negative numbers, so I can actually create tables right above it. X, m, and x, m. This is 9, 10, 11, and 12. This is 6, 7, 8, and 9. And this over here is 0, 1, 2, 3, 4, 5, 6. And these are its values. Once you plot those into that equation, this is negative 170, negative 180, 190, 200, 210, 220, and 230. This guy over here is negative 230, negative 200, negative 170, negative 140. And last one is negative 90, negative 60, negative 30, and 0. These are the points that I would like for you to pay attention. At 6 and 6, same number. However, 9 and 9 do not yield the same number. So that's okay. We're going to plot these points. This is linear, this is linear, and this is linear. So we know we have straight lines between 0 and 6, 6 and 9, and 9 and 12. So if we say that this is negative 50, negative 100, negative 150, negative 200, 250, 300. So we start at negative 170, which is around here. And we're going to go all the way down with a slope of negative 10 to negative 230, which is around here. Straight line. we start at negative 230, which is here. And again, at 9, this is again a straight line with a slope of positive 30. We go down to negative 140, which is around right here. Negative 140. All right. Now this one begins at negative 90, which is actually right around here. Negative 90. And it goes all the way to 0. It also has the same slope of 30. So we start at 0. And from the original drawing, if you recall, we have a reactive moment at A whose magnitude is 170. So one way to look at this, reactive moment at A 170, and that is the reactive moment is positive. It's counterclockwise. That's MA. Counterclockwise, produce an internal load that is negative. That's why we are negative 170. So one way to look at this, and there's several ways of explaining this. Ms. Ramirez has her own ways. I have my own ways. Basically, positive moments or external produce, this is positive, they produce negative negative internal loadings. That's why, even though it's positive 170, it produces negative 170. And that's exactly what we see here, guys. This is so important. There's an external moment of 50, which is negative. Clockwise is considered negative to us. So internally it's producing counterclockwise resistance, if you want to call it. So a negative produces positive, and that's why we see this jump going up of 50. So it goes from negative 142, this is negative 90. That's the jump that needs to be explained. And those jumps are only produced by those moments. So again, we start at 0, we end at 0. Whatever external loads that you see here, external loads, as far as moments, only the moments, not the point loads. If they're counterclockwise, they produce positive shifts in our moment diagram. If they're clockwise, such as this guy right here, they produce negative shifts in our moment diagram. Right? I hope this was of benefit to you. I'm actually going to create another video right after this in which I will use the graphical approach to solving this exact same problem. And it's going to be basically a fraction of the time that it takes you to solve this same problem by equation method. I hope you enjoy. Thanks.